talk about how oxygen is carried in the blood and how hemoglobin is involved in the transport of oxygen, and also some other ways that oxygen is carried in the blood. Well, the first thing we need to say is that oxygenated blood has 98% of its oxygen bound to the protein in your blood called hemoglobin, and only 2% of it is dissolved in the plasma, just dissolved in the plasma itself as just dissolved oxygen. And just in comparison, about 7% of carbon dioxide, of the total carbon dioxide that's in the blood, is dissolved in the plasma. So again, these numbers are not going to mean that much to you, so don't worry about them because I don't want them to confuse you. But 98% again of oxygen that's in your blood is going to be bound to hemoglobin, and only a small percent, 2%, will be dissolved in the plasma, whereas 7% of the total CO2 that's carried in your blood will be dissolved in the plasma. We'll get to more talking about CO2 in just a little bit. So this picture here we're going to be talking about later. This is basically showing you how oxygen is picked up at your alveolus, it's brought in, it's carried by hemoglobin, it goes through the systemic then capillaries, and then the hemoglobin lets go of the oxygen, and then it goes into your peripheral tissues. So the more oxygen that there is in the plasma, the more of it will be bound to hemoglobin until the hemoglobin molecule is what we call saturated. So we want to remember the structure of hemoglobin, and hemoglobin is composed of 4 polypeptide chains that are make up this globular protein, globular because it's shaped like a globe. So there are 4 different polypeptide chains. You can see the 2 lighter colored ones here and the darker ones here. So we have 2 alpha chains and 2 beta chains. Each of these polypeptide chains contains what we call a heme group, this little pigmented thing. This is a pigment complex. And at the heart of this little pigment complex is an iron atom. It is a reduced iron atom, meaning that it is it has more electrons. It doesn't matter right now, just so that you know, remember that oxidation versus reduction. But at any rate, it has an iron atom in the middle of it. And so there are 1, 2, there are 3, 4 heme groups and 4 iron atoms, and each of these hemoglobin molecules, the whole thing, can bind 4 oxygen molecules, and the oxygens are going to bind to this heme group. So each oxygen molecule, O2, can bind to each one of these heme groups. The more oxygen that's in your plasma, I'll say this sentence again, the more can be bound to hemoglobin until the hemoglobin is fully saturated with oxygens, meaning it is carrying all the possible oxygen that it can carry. And I'll say it again now, the more oxygen you have in your plasma, the more is bound to hemoglobin until the hemoglobin is saturated. And this is what we call a hemoglobin dissociation curve. And this is showing you the y-axis, it's the percent saturation of hemoglobin. 100% means that all of your hemoglobin is 100% saturated or filled with as many oxygens as it can hold. Down here means only 10% would be. So we can look at the graph and see what the saturation is. Now this x-axis is the PO2, or the partial pressure of oxygen. So as we see, the more oxygen there is, the greater the partial pressure of oxygen. As we increase from 0 to 100, we can see that there's an increase in the saturation of hemoglobin. And the hemoglobin is such chemically that it will bind it in this kind of a S-shaped curve. And why does it do it that way? Well, let's look at this graph again. This hemoglobin or oxygen hemoglobin dissociation curve is a graph of hemoglobin's saturation, or its affinity for oxygen, as a function of PO2. So what happens to hemoglobin saturation as you increase PO2? Remember, saturation of hemoglobin is how many oxygens can it hold. So as your PO2 increases, that's your partial pressure of oxygen, as it increases here, you can see that hemoglobin saturation will increase as oxygen increases. And each loading of each oxygen to a hemoglobin molecule will actually increase the affinity. Affinity means the attraction for more O2 molecules. So it causes this very steep shaped curve that's shaped like an S. It's a very steep slope going from the very beginning, because every time a little bit of oxygen binds, that makes the hemoglobin even more willing to grab more oxygen. It has a stronger attraction for oxygen as with each one that that all of these hemoglobin molecules grab. They have an increased affinity until they get to a certain point. Once you get to the point where the hemoglobin molecules are pretty well saturated with oxygen, then the slope will flatten out. It won't increase as much. So I ask you, why the steep slope? Why this steep region? It's because of this increased affinity of hemoglobin. With every every oxygen that binds to hemoglobin, it makes it even more attractive to oxygen. It has a greater desire to grab a hold of oxygen until it reaches this plateau region, which the flatter slope here indicates that hemoglobin is just about 100% saturated. It's getting real close. So you cannot increase the oxygen as much as you want. You just can't get it to hold anymore because it simply can't. All right. Now, let's think about what happens at the alveolus. Okay? At alveolar PO2, and if you want to think back to the diagrams that we've drawn, in the alveolus, the PO2 is going to be fairly high, like around 100. So at like about a PO2 of about 100, the percent saturation of hemoglobin is going to be really high, like about 97.5%. So it's going to be really high. At a PO2 of about 60, it's still, let's see, here we are at 60. Let's go up here. At 60, it's still even going to be about 90% saturated. So this is a very wonderful thing about hemoglobin's chemical structure, that it acts as it does. So that even at a much lower PO2, your hemoglobin is still pretty well saturated. It's a very good thing. Now let's think about the tissues. At tissue PO2, remember at the tissues it's around 40. The PO2 is around 40. Hemoglobin, okay, so let's go. Here's PO2 of 40. So let's just go up here and go, okay. At a PO2 of 40, hemoglobin is only about 70% saturated. At a PO2 of about 20, which is much, much lower, the hemoglobin saturation drops way down to about 30%. So this is the we're in kind of the steep zone here. So okay, so let's leave that as it is. So the point that I want to make is that at tissue PO2, which is fairly low, hemoglobin will give up oxygen easily. It has a low affinity for oxygen, and that's a good thing. because at your tissues need oxygen. So the shape of hemoglobin chemically is such that when it is at tissue PO2, it will give up oxygen relatively easily, meaning it has a low affinity for oxygen. Okay, now we're going to ask you a question here. Why are these slopes different at different pHs? Let's see. Here's the effective pH. So normal pH of blood is about 7.4. Low pH, which means acidity of blood, here's the 7.2, the green line. And more alkaline pH, a higher pH at this yellow line, is about at 7.6. And we can see that the dissociation curves are different with different pHs. And we can also see that there's a difference with different body temperatures. Well, let's investigate this. So we must know that the affinity of hemoglobin for oxygen, how attractive, how much hemoglobin would like to grab oxygen, the affinity, is affected by pH, temperature, and whether we're talking about fetal versus maternal hemoglobin. Well, let's first talk about the pH effect. At the lower pH, meaning higher CO2 levels, the more CO2 we have in our blood, the lower the pH, and we learned about this in A&P 1. This will be something that we'll discuss in class just to make sure you understand it. But when you have higher CO2 in the blood, that gives your blood a lower pH. And at lower pH, the hemoglobin has a decreased affinity for oxygen, meaning it will give it up more easily. So high CO2 in the tissues, low pH, hemoglobin gives up oxygen easily. And again, that is beneficial for the body because when your body is low in CO2, it is good that hemoglobin wants to give up its oxygen. This is just because of its shape. Now, at higher pH or lower CO2, hemoglobin's affinity for oxygen is increased. So in the lungs, when we have a lower CO2 level, hemoglobin will take on oxygen because it has a greater affinity or a greater attraction for oxygen. Again, this is very beneficial that hemoglobin does this because in the lungs, that's where there's lots of oxygen, and it happens that hemoglobin has a greater affinity for oxygen at lower CO2 levels, which is how what the conditions are in the lungs. So now with temperature, let's see what happens. Well, in your tissues, increased temperature will cause decreased oxygen levels in your blood, the oxygen saturation. And why is that? Well, active tissues that are actively metabolizing will have a higher temperature, and this then will cause more oxygen to be released to the tissues. Hemoglobin will tend to release oxygen to the tissues at higher temperatures. Let's look at this again then. First, let's look at the pH effect. There's our normal brown pH of 7.4 in regular kind of normal blood. Now, in the actively metabolizing tissues, the pH would be 7.2. And so let's just kind of look at if the percent hemoglobin saturation is 80, right about here for in normal pH of blood, when we see at 80 what happens to the excuse me, I should go the other way, forgive me. Let's just look at 60%. Let's look at about let's look at about 60% PO2. So right here, I'm going up to the pH of 7.4, and there you go. Here is your hemoglobin saturation is up here at about almost 90% at 60. But if we change the pH at 60, we can see that the hemoglobin saturation is lower on the green line where we have active metabolism. And that lower saturation means that hemoglobin, its behavior is that it will give up oxygen more easily. It has a lower saturation, meaning it lets it go into actively metabolizing tissues. So the curve is shifted to the right in actively metabolizing tissues that have a lower pH. Whereas if we are in the lung tissue where the pH is higher, this will move the curve to the left, and this will show that the hemoglobin is actually has a stronger affinity for oxygen. So if we again go to 60, right here, there's 7.4, and then if we look at 60, we can look at this yellow line right up there. We can see that the hemoglobin saturation, if we move over, is actually above 90%. So hemoglobin tends to hold on and grab oxygen. It has a greater affinity for oxygen at a higher pH. All right, if we look now at the temperature effect, we can see, let's look at what normal body temperature is, about 37 degrees centigrade approximately. If we raise the body temperature to 43 degrees, this is what happens to the hemoglobin dissociation curve. We can see that if we, let's just go to 60, we'll go up and look at normal body temperature. Here we go. We lean it, take it over here. It's about 90. We come back, and then at higher body temperature, we can see that the hemoglobin percent saturation is much lower, in the 80 some or 70 some percent range, and that means hemoglobin is releasing oxygen to tissues that are having a more active metabolic rate at 43 degrees centigrade. And then if we look at colder body temperatures, we can see that this, let's say at a PO2 of 60, we can see that we will have, again, the curve is higher. We go over here, we can see that we have a higher level of hemoglobin saturation, and even higher, again, as we look at even colder temperatures, meaning that at cooler body temperatures, hemoglobin will hang on to and will have a strong affinity for oxygen and will not release oxygen to the tissues. And that's good. It doesn't really, the tissues don't really need oxygen. They're very slow. Of course, these would be very cold body temperatures. Those are just kind of theoretical temperatures. And then as far as fetal versus adult hemoglobin, let's look at first let's look at adult hemoglobin. This is just mom, and if we look at a point right here, let's say at about 40, we can see that the point of mom being at 40, and we look at fetal hemoglobin, mom's level here is right over here, and if we look at 40 in the fetus, the fetus has a much higher affinity for oxygen than the mother's hemoglobin does. So fetal hemoglobin is going to grab oxygen, and this gradient, or this difference in affinity for oxygen, is very important, because that means that oxygen will tend to diffuse from the maternal blood to the fetal blood, and that's good because the fetus needs to have the oxygen being transported from the mother to the fetus. Okay, this is a good place to stop, and I thank you for your attention.